All right, welcome back, folks. We're going to talk about what's called the law of conservation of energy here to wrap up section 2. So the law of conservation of energy is very similar to the law of conservation of momentum. Energy, it states that whatever energy that we have cannot be created or destroyed, but instead is going to be either transformed or it's going to be transferred from object to object through the process called work. So the key idea here is that the amount of energy that we have within an object or within a system is always going to be conserved. Unless that object is going to face some sort of force, like an external force that's going to take that energy away or potentially give it more energy. And that's the idea of energy being transferred. So this is kind of applying what we learned about already with the work and the whole types of energy, that when I do work, I'm going to add it in the form of, let's say, potential energy, that let's say I give it gravitational potential energy, that then when I let that object just naturally use that energy, that it's going to use it in the form of motion, which is kinetic energy. So it's the idea that first, when we do work, that we are transferring energy into that object. So that, again, is done through the process of work. And if you remember, work is going to be applying that force over that distance, and again, considering the angle between the two. But the key thing here is that the conservation of energy is really going to apply to the idea of energy being transformed. Transformed means that if I give, let's say, an object 100 joules of energy, that 100 joules of energy can be given in certain forms. One, it can be given in terms of all potential or all kinetic. But if I let an object naturally use that 100 joules of energy, that what's going to happen is it's going to transform itself from type to type. So let's say that I have this skier going over a hill. Obviously, if the skier going up the hill, it's got to have some speed to it. So let's say here that has some kinetic energy because it's maybe has a little bit of height, it's got some potential. What we know is that let's say that I give it 100 joules. Now, just to fit kind of some numbers to it, let's say that it has 90 joules of kinetic and 10 joules of potential, such that that would add to a total of 100. What the law of conservation of energy states that if I have 100 joules of energy beforehand, I should have 100 joules of energy afterwards. But what happens as the skier goes up the hill is that their speed naturally is going to decrease, that they're going to slow down naturally because of gravity. But what this means in terms of energy is that they're slowing down, their kinetic energy is decreasing. So let's say that their kinetic energy goes from 90 down to 10. So that's a loss of, let's say, 80 joules of energy. But where does that 80 joules of energy go? But obviously, as it goes up the hill, it's gaining height. So the 80 joules that was lost as kinetic naturally goes into potential energy. So I know that that would go to 90, so that, again, those two would add to 100. And this idea right here is what's showing the law of conservation of energy, is that energy is going to stay the same. Same idea can be seen in reverse. Let's say that I give it a lot of potential energy to start, goes down the hill, it's going to lose height but gain speed. So if it gains speed, again, it's going to gain that speed or that energy from somewhere. So the idea is that the amount of potential energy that it lost in the initial phase is going to go towards the kinetic energy that it's going to have in the final phase. And that's the idea of energy being transformed. So we can apply this idea of the law of conservation of energy to solve problems very similar to one that I just showed you. So let's say that I have a 50 kilogram skier on top of a 100-meter hill, such that because the skier's got height, we have 50,000 joules. Again, that would just be solved by doing the whole m times g times h. So if I took the 50 kilograms times gravity, which is 10, times the height, which is 100, that'd give me 50,000. Skier starts at the top, so let's just say it starts with no kinetic energy, so it's not moving at the top. So we can use this idea of transformation of energy to try and solve problems. So let's say we have the same kind of skier now. Let's say a skier starts on top of a 100-meter hill. They got a mass of 50. So if I want to think about gravitational potential energy using mass, gravity, and height, that'd give me 50,000 joules. Again, 50 times 100 times gravity, which is 10, would give me 50,000. Say they're not moving. The idea is that here I have a grand total combined of 50,000 joules of energy. Okay, this is sometimes called, I'll label as TME. This is called the total mechanical energy of a system. Okay, so in this case, the total mechanical energy is going to be equal to 50,000 joules. And as the skier goes down the hill, they're going to lose height but naturally gain speed. So again, if you look at the values of potential energy and kinetic energy, here is going to still add up to 50,000 joules. So therefore, down here is if they have a height at, or sorry, if they have a potential energy of 15,000 joules, and then in this case, that means that their kinetic energy would be 35,000 joules. And again, why 35,000? It's got to add up to 50,000. So then when the skier goes up the hill, as they go launched from this hill, it's going to gain height, and as they gain height, they're naturally going to lose speed. So this would be that projectile motion stuff we talked about, that here if they're at a height of 60 meters, using this idea here, if I did the whole mass times gravity times height, where the mass is 50, height is 60, g is 10, here they're going to have 30,000 joules of potential energy. And notice that because here they're at the same height as over here, notice that I have the same amount of potential energy, and therefore the kinetic energy, because it's got to stay totaled to 50,000, should equal 20,000 joules. And then at the bottom, here since they have a height of about 0, I know they're going to have 0 joules, which means all of that energy, that entire 50,000, is all in the form of kinetic. So what I see here is just kind of a give and take between kinetic and potential energy, such that the total mechanical energy always stays the same. This is what's called the law of conservation of energy. Okay, we can apply that same idea then. Here you're kind of given the values for each one. So this is a pendulum. So at 1, 2, and 3, at 1, obviously it's not moving. As it starts to swing downward, it's going to gain speed to at 3, where it's going to have its maximum speed. And in 4, notice it's not moving again. The idea is this, though, is that if you look at part 1 and part 4, because they're at approximately the same height, that means they both have the same energy. So looking at it, we can track potential energy starts off at 6 joules. As it swings down, it loses height, so it's going to go from 3 to 0, then back up to 6 as it gains height. As it loses potential, obviously kinetic is going to go from 0 up to 3, then up to a maximum of 6, and then back to 0. So again, the total energy that we're seeing here is always going to add up to 6 joules, and that's the idea of the conservation of energy and energy being transformed. What we can do now is we can use this to try and solve. So you're given here that in this problem, let's say the pendulum bob has a mass of 2 kilograms. So let's say I want to know the height and the speed at these respective positions. So in this case, if I know that it has 6 joules of potential energy and I want to find the height, then I can use that mgh relationship is going to equal our potential energy. So if I know that it has 6 joules, I know the mass is 2, gravity is 10, what height would that reach, or what height would that start at, in order to get that 6 joules of potential energy. So in this case, I know the height is going to be 0.3 meters or 30 centimeters, if you will. Okay. Then when it swings down, again, we can use both these relationships to find height and speed. So I can do the same thing here in the second case, that if it has 3 joules of potential energy, and I know the mass is 2, g is 10, what would be the height here? So the height in this case would be simply half of what it was before, so that's going to be 0.15 meters. And again, that's just due to because it has half the energy, it's probably going to be at half the height. But then now I can use the whole kinetic energy equation as well and know that kinetic energy, I'll write it up here, is equal to 1/2 mv squared. So if I want to solve for the speed, I know it's got 3 joules of kinetic energy. I know the mass is 2, so I can go ahead and solve for v. So again, you can use the algebra here, just so I got some more real estate. Let me move that up. But if I solve for v, not the prettiest of answers, but you're going to get a speed of about 1.73 meters per second. Okay. Then we can continue on again, solving for the height and the speed at these individual positions. So if it has 0 joules of potential energy, I know that here the height is going to be 0 meters. Therefore, what would the speed be? So again, it's going to be all 6 joules is going to go towards kinetic energy. So I can solve for the speed, and I know in this case it's going to have about 2.4 meters per second of speed. So notice as it swings down, it's gaining speed. And then lastly, in position 4, height and speed, I know at that position it's going to have a speed of 0 because it's at that maximum height. And because 1 and 4 are about the same positions, that I know the height here is going to be the same thing as it would be for position number 1. So I know the height here is going to be 0.3 meters. So this is the idea of what's called the law of conservation of energy, that it's just a transfer of kinetic and potential, but what it allows us to do is solve for the idea of height and speed where we might have had to use different relationships prior to this unit. All right, if you guys got any questions on the law of conservation of energy, jot those things down. We'll see you in class. Peace.